So, how do we get pressure from quantum mechanics? I'm going to do a very approximate, very rough calculation to show how a white dwarf can work. The full calculation is too complicated for this course, but we can get the basic physics and a roughly right answer out by making some big approximations. So let's start off by thinking about electrons stuck in a box. This box could be 1 cubic meter of white dwarf material or 1 cubic meter of anything really. And let's assume we have a number of electrons per unit volume, so a number density of electrons of Ne. So that's the number of electrons per unit volume. Now, all the electrons can't be in the same space because of the Pauli exclusion principle. They all have to have their own discrete identity. They can't all sit in the same state. So each electron, so we've got an electron there, has to have its own unique volume. So let's assume it each has a cube like this. As the electron is trapped in that volume, it's going to the size of this volume, the size of each side here, is the uncertainty in its position, delta x. And what is delta x? Well, each electron has a volume delta x cubed, that being the volume of a square of each size delta x, and there are Ne electrons in 1 unit volume. So what that's telling us is that delta x is equal to 1 over the cube root of Ne. So that's Ne to the minus a third. Now if we have that uncertainty in its position, that means there's going to be an uncertainty in the momentum. So the uncertainty in the momentum times the uncertainty in the position is going to be h bar. That's Heisenberg uncertainty principle. So the uncertainty in the momentum is going to be h bar over delta x. So that's going to be h bar Ne to the plus 1/3. So that tells us that the electrons are not still, they have momentum. There's an uncertainty in it. And that's going to be roughly equal to the momentum. Some are going to be going forwards, some are going to be going backwards. This is the momentum in one direction. So roughly speaking, the uncertainty is going to be about the size of the momentum. So roughly speaking, again, not a very good approximation, but close enough for this work, the momentum is going to be about the size of the uncertainty, and it's given by this.